All right. I wanted to talk about these free body diagrams because you are going to see this and these concepts on the exam. This will be a big part of the exam, actually. So in prompt 1, you had a baseball player sliding into base. So this is based on the balanced and unbalanced force app game that you have access to in your course, and this is basically taken straight from it. So imagine that baseball player. When he comes sliding into the base, he is no longer pushing himself forward, but he is moving forward because of his inertia. And the only reason he comes to a stop is because there's friction between him and the ground acting against him. So he's touching the ground, he has weight, and he has the ground pushing back up on him, balancing the weight, so he has weight and the normal force. And he's coming to a stop. If he's moving to the right, that means that the only force acting on him because he's skidding to a stop is friction. So if we were to plot his motion on a dot diagram, every second, because he's slowing down, he would go less and less distance. So after 1 second, maybe he's traveling 20 meters per second, then 15 meters per second, then 10 meters per second, then 5 meters per second. So every second he goes less and less distance. So the dot diagram is getting, is dots going to the right, getting closer because he's slowing down. For the basketball that's launched into the air, where air is negligible, when it's up at the top, there's only one force acting on it, and it's weight, because it's in free fall. That is the definition of free fall. So just like in your lab where they threw up all those different objects, the only force causing them to slow down on the way up and on the way down is weight. So there's only one vector. So as it falls downward, it's going to speed up by 9.8 meters per second every second. So that means it goes faster and faster every second, and so the dots would get bigger and bigger. If we were drawing the diagram on the way up, it would be slowing down by 9.8 meters per second every second, so it would go less and less far, so the dots would be getting closer to each other on the way up and further from each other on the way down. In prompt 3, you're pushing a box, and I'm telling you that the pushing force is 30 newtons and the friction force is 30 newtons. So anytime a box is on a surface, it has weight, and the weight is being balanced by a normal force. That means that there's a force pushing it to the right of 30 newtons and a force acting against it to the left, friction, of 30 newtons. Notice that in this diagram, all the arrows are the same size. They are balanced, which means that this is in equilibrium. So even though it's moving, all the forces are balanced, which means that there is no acceleration. It will be traveling at a constant speed. A dot diagram for something that's traveling at a constant speed are dots that are equally spaced. So if I was traveling at 50 miles every hour I would go 50 miles. The dots would be exactly the same distance every hour, 50 miles apart. And then finally, another example of constant velocity is something that has reached terminal velocity, which only happens when the air drag balances out the weight. So once again, it's got downward force of weight acting on it always, but because it's reached terminal velocity, that tells me that air is a factor and it is balancing the weight. So as it falls, it no longer accelerates. It travels at whatever speed or terminal velocity it has at a constant rate, so the dots are equally spaced. So the big thing for you to realize is that when forces are balanced, like in prompt 4 and prompt 3, there is no acceleration. And the dot diagram is a diagram with equally spaced dots. But when forces are not balanced in prompt 1 and prompt 2, the forces are not balanced in this because there's nothing balancing the friction force. And the direction of acceleration is always going to be in the direction of that net force. So if the net force is to the left, then the acceleration, the speeding up, would be to the left. The problem is that this object is trying to move right. So if you look at its motion, instead of speeding up, because it's moving to the right, it will be slowing down. So a dot diagram that has dots that are unequally spaced, the dots get bigger in the direction of the net force, and that's the direction of speeding up. If the object is trying to move in the opposite direction, so as I go to the left to the right, I see the dots are getting smaller, it would slow down instead. So in prompt 2, the net force is downward, so the speeding up, the acceleration direction is downward, and the dot diagram, the dots get bigger in the downward direction. I strongly urge you to play the balanced force game, because it goes through all sorts of scenarios where you look at diagrams and you decide whether the forces are balanced. And if they're not balanced, you can determine whether it's speeding up or slowing down. It's really important for you to do that, and you will definitely have that on the exam.